Yeah, thank you. Alright, so welcome to part 2 and let's get back to what we were, right? So in the meantime I've written down some of the things that we actually proved without writing in the discussion, right? So this is an exercise actually. You have a matching code graph, a tight cut and C contractions, and the first statement is what we just discussed. The dependence relation of Gi is simply the dependence relation of G restricted to the edge set of Gi. And the second one is that any equivalence class intersects any tight cut in either 0 or 1 edges, right? That's for an equivalence class, you don't need the minimal class. The second statement here, this is for the same setting, matching code graph, tight cut, and G1 and G2 are the C contractions. Now Q is a minimal class, and what we proved is that if you look at restriction of Q to G1, either you get the empty set or you get a minimal class of G1, right? So that just follows from the first statement here. And in particular, if a minimal class has empty intersection with a tight cut, then the entire class is either in G1 minus the cut or in G2 minus the cut, right? So these are some facts that we just discussed and proved, right? But you can write down complete proofs of them later to convince yourself that there is no mistake there. Yep. So anyway, so these are things we know, and what we did is we observed that to prove theorem 8.17, first of all we have already proved it for bipartite matching code graphs and bricks, right? That was what we did in the first part of the first part. And then we discussed the proof attempt of theorem 8.17. So we are done with bipartite graphs and bricks. So now assume you have a graph that is neither bipartite nor a brick. In particular, there is a non-trivial tight cut. And we observed that the only case, using all of these facts, the only case where we are not able to finish the proof is this case, where the minimal class has exactly 3 edges, one on the left, one on the right, one in the middle, in the cut. Right? And now you look at Q1, it is a minimal class, but the cardinality is not 3 or more, therefore you cannot apply the induction hypothesis. You look at Q2, minimal class, again cardinality is exactly 2, and you can't apply the induction hypothesis. In all other cases, you are done by induction. Yeah? Okay? Alright, that was proof attempt. Now we come to actual proof. And you will see manifestations of all this discussion in the actual proof. And we will not finish the proof today, but we will make some progress. So, instead of looking at an arbitrary tight cut where we got stuck in that case, so actually that brings me to an important point. Is there a way to finish the proof from here? I do not know, right? Can we somehow do something and still finish the proof without using more sophisticated things, 8.13, which is what we will use now. Okay? So, we have a matching code graph, we have a minimal class whose cardinality is 3 or more. So, suppose that the cardinality of Q is at least 3, and let E1 and E2 be distinct edges. I mean, I'm tempted to write this because every edge depends on itself, right? So, yeah, so E1 and E2 are distinct edges in this class. So we can apply 8.13 because they are mutually dependent. We have this figure with E1 and E2. We have a barrier in G minus E2 that contains both ends of E1, and the edge E2 looks like this. If I put it back, then I have this figure. And we know some facts. We know that actually there are no even components in G minus E2 minus B. There are only odd components, these 5 odd components that you see in this figure. and each odd component is the shore of a tight cut. Yeah. Okay. So what I want to do next is, I want to apply all of the knowledge we have from here to here. But now we don't have just one tight cut. Now we have 5 tight cuts. Some of them may be trivial, admittedly. I want you all to tell me how many of these odd components can be non-trivial. Right? Knowing that if we are ever in a situation where this is not the case, then the proof is actually finished. This is the only case. Note that all of these are special cases of the general proof that we did here. You have a non-trivial tight cut. You have all the other hypotheses satisfied. You have a matching code graph. You have a minimal class of cardinality 3 or more. So what I want to do is, I want you all to think about what is the case we got stuck in, and what does that imply about this more sophisticated situation. Here we have more information, right? Right, so that's what I want you all to think about. How many non-trivial components can we have? So that's the main question. DIY for now. How many non-trivial odd components, well, all components are odd, in G minus E2 minus B? And the point is, if that is not the right, that is, if supposing you tell me there are k non-trivial odd components, that means in all other cases you should be able to finish the proof using this argument, right? So in all other cases we are done by induction. In fact, what do we know about the cardinality of Q? The only case where we are not done by induction. Huh? Q, 3. The only case where we are not done by induction using this proof attempt, which was completely valid, right, is the case where Q has cardinality 3. So that's another point. For this proof, because of whatever we have done, we can actually assume that cardinality of Q is exactly equal to 3. We just need to finish the proof in this case. In all other cases, you go there and you finish the proof there. You don't need this more sophisticated figure. That's the point. Okay. So we have exactly cardinality 3 for Q. And now my question is, how many non-trivial odd components? And what does the figure look like? The figure where we are not able to finish the proof right away. Okay? So the point is that all of these are shores of tight cuts, non-trivial or not, they are shores of tight cuts. If any of them is non-trivial, then what you have is a non-trivial tight cut, and then it must contain one of the edges, one of the pink edges. There are only 3 pink edges, E1, E2 and E3. Right? Let me actually put down, we are in Q equal to 3 case because all other cases are done. So let's say the 3 edges are E1, E2, E3. Right? These are the 3 edges. So if any of these components is non-trivial, then it follows by what we have done earlier that that non-trivial component should contain the third edge, both ends of the third edge. Well, but there is only one third edge. So there is only one non-trivial component if there is. So therefore there are either 0 or 1 non-trivial components. Yeah. So by our earlier discussion, G minus E2 minus B has 0 or 1 non-trivial components. Yeah? And we are not done with the 0 case. We need to work on the 0 case. What we will do today is we will finish the 0 case. And tomorrow, or sorry, Wednesday we will finish the 1 case. Yeah? So, case 0. So, let's make a drawing of case 0. We have one edge like this. And we have one edge like this. Right? Where is the third edge? I don't know. It is somewhere. This graph is almost bipartite, but don't mix up with near bipartite. It's not that. G minus E2 minus, G minus E1 minus E2 is bipartite. In fact, it is definitely not near bipartite, because for near bipartite you need G minus E1 minus E2 to be matching covered, but it's not matching covered, right? E3 is not matchable in that graph. Right? E3 is in the same class, therefore if you delete these 2 edges, then E3 is necessarily unmatchable. In fact, we can actually conclude that E3 is the only unmatchable edge in G minus E1 minus E2. In fact, E3 is the only unmatchable edge in G minus E1 minus E2. Right? And this graph is a bipartite matchable graph. You all agree? G minus E1 minus E2 is not only bipartite, it is also matchable. Right? There is definitely a perfect matching. Yeah? But there is one unmatchable edge. That fellow is E3. Let's finish this proof. Now, DIY. Try finishing the proof right now. Make a drawing. Make a drawing, count and conclude. It's just counting at this point. That's all there is to it. There's nothing more than counting. I want to make one more statement. If G minus E1 minus E2 is disconnected, we are done. There's nothing to prove. If G minus E1 minus E2 is disconnected, then actually there's nothing to prove. You have deleted two mutually dependent edges and you have disconnected the graph. What can you say about the order of the components, given that the two edges are mutually dependent? They have to be of even order, right? Mutual dependence. They have to be of even order. Here we are not even using anything else, right? In fact, I could have made this statement much earlier in life. I could have said here itself, in the very beginning we could have said, if G minus E1 minus E2 is disconnected, then E1 E2 is an even to cut. It can't be an odd to cut. Then they would not be mutually dependent. Is an even to cut. And there's nothing to prove. So you can also assume at this point that this is a bipartite matchable connected graph. All these things you can assume. This actually significantly reduces the number of cases that are actually worked out in Lucchesi-Murty. So Lucchesi-Murty have 4 cases, but if you assume all of these things, significant number of those cases are actually out. They don't happen. Okay, let me know once your drawings are ready. Yeah, so it's worth noting that the graph is definitely not bipartite. You have a bipartite connected graph, so its colored classes are actually uniquely determined, let's say black and white. One edge, let's say E1, has both ends in one color class, that actually already creates an odd cycle, and the other has both ends in the other color class. So, yeah. But it is tempting to hope that the graph is bipartite. Right, so use the fact that E3 is the only unmatchable edge. Right, I think I wrote that somewhere. E3 is the only unmatchable edge in G minus E1 minus E2. That means that in your drawing, there would be no other edges going from top left to bottom right. Right? Because if there were other edges going from top left to bottom right, they would also be unmatchable, which we know is not true. Yeah, remember E1, E2, E3 all belong to a perfect matching, or none of them belong to a perfect matching, given any perfect matching of the graph. That should also help you in the counting. This is your drawing. You actually have two bipartite matching covered graphs with only one edge joining them. This is the only unmatchable edge. That means, and it is a connected graph. So if I delete this edge, I will get exactly two components. They are actually matching covered, right? Because this was the only unmatchable edge. So this is the edge going like this. This is the only edge in the graph G going from A0 to B1. There are no edges in G going from here to there. And the only other edges joining these two boxes are the edges E1, whose both ends are in B, and the edge E2, whose both ends are in A. I don't know whether they go like this or like that. Yeah, you all agree? So that means that E3 is already part of either a 2-cut or a 3-cut. In fact, I am going to do as little work as I can. Right? E3 is already part of either a 2-cut or a 3-cut. Yeah? Because once I delete the two edges, it is a 1-cut. Right? So either it is a 2-cut, in a part of a 2-cut or part of a 3-cut in the graph G. Well, the only way to be part of a 3-cut is if the edge E1 goes like this and the edge E2 goes like this. Right? Don't worry about the ends, doesn't matter. But then there is a perfect matching containing E1, E2, E3. That's not possible. How is there a perfect matching containing E1, E2, E3? Right? In fact, they should be a non-adjacent, right? This is not even misleading because it is a class. The three edges are pairwise non-adjacent. So how will you get a perfect matching containing these three edges? Right? If there is a perfect matching containing these three edges, so I am taking this edge, and this edge. Now I have to match these two vertices here. 1 to 2 to 1, and here I have 3 going to 2. There are no other edges in the cut. This is the whole drawing. And that's not possible. So therefore, it cannot be this. Therefore, it must be that E3 belongs to a 2-cut with either E1 or with E2. Therefore, Q contains an even 2-cut. Also, it is an even 2-cut. Q contains an even 2-cut. One of the edges is E3. In some sense, we got unlucky when we chose E1 and E2. We should have chosen E3. Right? E3 is there in the even 2-cut. Right? So that's basically what this is showing. That we just got unlucky in our choice of E1 and E2. Which brings me to another question. Is there a way to make the proof by choosing E1 and E2? In fact, I want to go back to this drawing. This example is really nice. Let's go back to the graph we had earlier. Here, we have a minimal class of cardinality n by 2, perfect matching, right? This is a minimal class with how many? 1, 2, 3, 4, 5, 6 edges. And you can see that there are specific edges that participate in an even 2-cut, but not any two. In fact, there are edges that don't even participate in an even 2-cut. Is that correct? I don't think this edge, for example, belongs to any even 2-cut, because when I delete this edge, I still have a 2 connected graph. Therefore, it is not in a 2-cut. Forget even. Right? So that's basically what is happening. The two edges we chose, we somehow got unlucky, and that is what the drawing is showing. That in fact we should have chosen E3 somehow. So is there a way to make this proof work by choosing two edges in the minimal class in a certain manner and then showing that hey, this is a 2-cut? In fact, another question is, given a minimal class, can you actually characterize all the even 2-cuts contained in that minimal class, assuming the minimal class is of cardinality 3 or more? Right? So these are all questions that kind of arise when you study the proof of this. Right? So we are done with the case where all components of G minus E2 minus B are trivial. That was our case 0. When all of them are trivial, we are done. The only case that remains is one component is non-trivial. All others are trivial. This is the case we will complete on Wednesday. Right? But but I suggest that before Wednesday you go through all of this again. So the approach that is taken in Lucchesi-Murty is they actually skip all of this discussion. They directly work with Theorem 8.13 and they directly deal with this situation instead of going through an arbitrary non-trivial tight cut, which I felt was in a way easier to understand without getting into this messy drawing. Just look at the general drawing that we have been used to, right? Just a non-trivial tight cut, see if you can finish the proof, right? Yeah, so anyways, try to go through it again and we'll complete the proof on Wednesday. Are there any questions or concerns? No? All good? Alright, in that case we may stop recording and continue on Wednesday.